In this lecture, we will continue the study of current transformers. We will study the effect of saturation and the transient phenomena in the current transformer. So, let us see what happens when there is a saturation in the current transformer. As I have told that if the burden is increased beyond a certain limit, like let us say if the secondary is open, that is burden is infinite, then there will be saturation of the CT core. Or if the burden is very high, so that the induced EMF EA is high in the CT, then we can see from the excitation characteristics that to get this higher EA, the flux required will be higher, and beyond the knee point, the flux requirement will cause the CT to go into saturation. Okay, so we see that whenever the burden on CT is more than the rated limit, then there is a situation where saturation can occur. Similarly, as I already told, if we open the secondary terminals of the CT, then again there will be a condition of saturation. Okay, now what happens? Initially, when the CT is working in its linear state, then we can see that it will faithfully try to reproduce the primary current in terms of or the secondary current in terms of the primary current according to the turns ratio. Okay, however, beyond this certain limit, any increase in current will require, or any increase in flux will require a very high increase in current. Okay, so that increase in primary current will just cater for the increase in the excitation current of the CT. That is, it will try to excite the CT to induce the required voltage through this flux. Okay, so we can say that the equivalent circuit diagram of a CT, if I again draw it here, let us say I am trying to draw the equivalent circuit diagram with all quantities referred on the secondary. This is the primary current. This is an ideal transformer. Rp prime, that is the equivalent primary winding resistance referred to secondary. XL prime for the primary. Okay, now this is the shunt branch for the core loss, and this is the excitation reactance. And here is the secondary winding resistance and secondary winding leakage reactance, and here I have connected some burden ZB. Okay, now here the current will be IP dash over N. Okay, if this is the number of turns ratio 1:N, let us say. Okay, so this will be current IO, and then this current IS, which is in the secondary or the burden also, will be equal to IP over N minus IO, or IP dash is equal to IP over N minus IO. Okay, so the voltage induced in the CT will be this ES. Okay, now this ES can also be written as IS into ZB plus Z secondary. Now if I merge this Z secondary into the burden only, then I can write it as IS ZB. assuming that the burden is also consisting ZS. Okay, so this is ES. So if this ZB is increased beyond a limit, then this ES will require a higher flux, since we know that E is equal to 4.44 NF phi m. So this phi m will be higher if E required is higher. Okay, so you see that it may cause the CT core to go into saturation. Okay, now let us say now the CT has gone into saturation. So any current which is flowing into the primary, which is referred now to the secondary side, will just go for the excitation part. Okay, that is, this branch will now act as a short circuit, and it is equal to IP over N, and this current will be now equal to 0. Okay, or it will be very small. Now there are two more points to notice, that increased core loss will also thermally damage the CT, as well as this there may be a danger of permanent saturation. Okay, now this is the equivalent circuit diagram of the CT during saturation, that is when CT is acting at some of this range of the excitation curve. Okay, now what happens into the, if I observe the waveform of the current or the ES, what happens to those waveforms? I am telling you that it will be peaky in nature at whenever there is zero crossing in the primary current. Okay, now let us see how we can say this. I will erase this first. Now let us draw the various waveforms involved. Okay, let us say this is the waveform for the primary current. Okay, now I am assuming that this waveform, if it is for IP, I am assuming that the CT is already in saturation. Okay, so you see that during saturation the CT will be operating in this part of the excitation curve. Okay, so a very small increase in phi will require a very large increase in the excitation current. So let us say this is the saturation level. For the CT, okay, that is, this is beyond this, if excitation current is there, then the CT will be in saturation. Okay, so after this point, the current waveform for the excitation current will be peaky in nature. Similarly, like this. Okay, similarly at this point we can see that the excitation current curve will be peaky in nature. Okay, like this, the excitation current will follow this waveform. I is the excitation current. I am not showing the loss component. I am just showing the magnetization component. Okay. Now, let us draw the picture of the flux. What happens to the flux? whenever there is a zero crossing. Okay, so from this point to this point up to the saturation part, the flux will follow the change linearly. Okay, because it will be acting in the linear region. So the flux will have a waveform like this up to this part, and after that the flux will be kind of constant. That is, flux will be like this, constant value in this region. Okay, now again here below saturation, the flux will again change to linear part and it will be decreasing like this. Then again the flux will be saturated here, then again it will reduce like this, then again it will be saturated here, then again it will reduce like this. Okay, so if I want to draw the waveform of the flux clearly, then I can shade it like this. So this is the waveform for the flux and this is phi m corresponding to this part. Okay, now let us draw the waveform of the induced EMF. Now induced EMF is proportional to d phi by dt. Okay, so here you can see that the change or the differentiation will be zero on these parts. Okay, differentiation will exist only during zero crossing. So I can say that from this part to this part, similarly from this part to this part, there will be some induced EMF. In this part and this part there will be zero induced EMF. Okay, now here the differentiation will be positive in nature, so the induced EMF will be positive. Okay, then here it will zero. Now here the differentiation will be negative, so the induced EMF will be negative like this. Okay, so this is the waveform for the induced EMF in the secondary or the primary. Okay, now if only resistance is connected as a burden, then the current will be ES over RB. So current will be also like this in the burden, having this waveform. So you see that during saturation CT will behave very abnormally and the relay connected, the burden connected will not get sufficient data or the right data to take any decision. Similarly, we can see that somehow if I reduce the level of these spikes, then in a metering CT it is a good thing because there will be no induced EMF across the metering equipment and that will be kept protected. Okay, so this is how the CT behaves during saturation. Now in the next slide we will see how the CT behaves during transient phenomena, because the relays have to act during the transient part only if they have to act very fast. Okay, so we should know what is the behavior of CT during these such kind of transient phenomena. Let us see that thing in the next slide. As I have discussed in one of my previous lectures while studying the response of an RL circuit to an AC excitation, that the power system is also can be considered kind of an inductive network only. So the behavior of power system to the AC excitation will be similar to that of an RL network. Okay, so in that lecture we have derived that the current during that phenomena or the fault or the transient will be of the form like this: I primary, that is in the power system, which is going to flow in the primary of the city also, will be V peak over R square plus omega L square, where R and L are the equivalent resistance and the inductance seen from the point of CT to the power system. Okay, that is R and L are equivalent resistance of power system seen from CT. Similarly, equivalent inductance of power system seen from CT. Okay, and then this part is consisting of two things. One is the steady state and another is the DC transient. Okay, sine omega t plus alpha minus theta. Okay, and plus sine theta minus alpha E minus t over tau, where tau is again related to this R and L. Okay, or tau is equal to L by R. Now, alpha is controlling the instance when the switch is closed in the RL circuit. Okay, this is the equation or the response of the current for this circuit. Okay, now this alpha is controlling the instance of the switching of this switch. Now theta is the power factor angle of this network. Okay, now we will try to just see the phenomena where the transient phenomena is maximum pronounced. That will happen when this part, the DC part, which is decaying with time, is maximum initially. So we are assuming that sine theta minus alpha is equal to 1, or theta minus alpha is equal to pi by 2, or alpha minus theta is equal to minus pi by 2. Okay, so to see the maximum impact, we will assume this condition. So IP can be written as Vm R square plus omega L square sine omega t minus pi by 2 plus E minus t over tau. Now I will write Vm over R square plus omega L square as Im. That is the maximum value of the current. Okay, so IP can be divided into two parts. Im sine omega t minus pi by 2 plus Im E minus t by tau. Okay, so this is the DC decaying component and this is the steady state component of the primary current, which is going to flow into the CT also. Okay, now this current will flow in the shunt branch or the magnetization branch of the CT. Okay, so this current will induce some flux. Okay, and because of that the voltage will be induced in the CT. Okay, so that there is a flow of current in the burden. Now as we know that phi is proportional to I and E is proportional to N d phi by dt. Okay. Now I know that E is simply the current into the burden, or if I take impedance, then I can write it like this: I secondary into the burden. Okay. Let me take that the burden is purely resistive to simplify the equations. Okay. Now I am also assuming that the CT is faithfully transforming the primary current to the secondary side. Okay. So, and this RB is the equivalent resistance seen from the secondary side. That is, RB is the equivalent resistance or equivalent. I am just assuming that it is resistive in nature seen from this point. Okay. And this is 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 equal to IP over N. Okay. So E secondary will be IM RB over N sine omega t minus pi by 2 plus IM RB over N E minus t by tau. Okay. Now we know that ES is equal to N d phi by dt, or I can write that d phi by dt is equal to ES by N, or phi can be considered as phi at t can be considered as, I am assuming that there is zero remnant flux initially. Okay. So phi 0 is 0. From 0 to t I will take this 1 by N ES dt. Okay. Now we will find these two components corresponding to this part. There will be an AC flux component. Corresponding to this part there will be a DC flux component. Okay. Now we will do this integration in the next slide. Now let us do the given integration. Now there is one thing to note, that this N I have already taken care of while finding this ES. So there is no requirement of writing this N now, because I am just finding the secondary side induced voltage and the respective flux. Okay, so this N has already been taken care of, so no need to write here. Okay, so first I will integrate this thing phi DC to find phi DC, and then I will integrate this thing. So I will integrate to find phi DC t equals to integration of this 0 to t IM RB over N E minus t by tau dt. Okay, so phi DC t will be equal to IM RB over N E minus t by tau into tau limit 0 to t. Okay, is equal to IM RB N. Now tau is equal to L by R. And there will be minus sign also. So it is equal to 1 minus E minus t by tau. To avoid confusion, we should have used a different integral variable. Okay, so I should write it at t dash and dt dash, t dash and t. Okay, so this is the equation for the DC component. Now you can see that it will have a waveform like this. It will increase from 0 and within the certain this according to this time constant, it will rise up to its maximum value at infinity equal to IMRB over N into LR. Okay, so this is phi dc tau and this is t. Now I will find the phi AC component. Phi AC t is equal to 0 to t IM RB over N sine omega t minus pi by 2 omega t dash dt dash, to avoid any confusion with the limits. So I am just taking the integral variable as t dash. Now I will perform the integration. IM RB over N minus cos omega will come here, omega t dash minus pi by 2, and this thing is going to vary from 0 to t. Okay, so it is equal to minus IM RB N omega cos pi by 2 minus cos omega t, or sorry, cos omega t minus pi by 2 minus cos pi by 2. Okay, so it is equal to IM RB, now this is 0 and this is equal to sine omega t, RB N omega minus sine omega t. Okay, so this is phi AC t. So this thing will vary according to this waveform. And its maximum value will be equal to IM RB over N omega. Okay, so you see that until unless there is a saturation, the total flux in the CT can be written as phi dCt plus phi ACT. After saturation we may not be able to write this thing. Okay, so I can club these two waveforms and I can write or draw the waveform for the total flux in the CT core. Let us do that. The flux will be kind of riding this on this. Okay, the mean value of the flux will change according to this DC value, the increasing DC value up to the transient, up to the saturation part. Okay, and this will be added on it. Okay, so their total sum will be found out using this. And the final value will behave like this. Initially it will be having 0, then like this, then it will increase like this, it will increase like this, and like this it will change. Okay, so after the saturation I cannot use this superposition. Okay, now you see that if I want to take the ratio of phi DC over phi AC, what it will be, the maximum value part, max, phi DC max over phi AC max. Okay, because infinity, instead of infinity, after 4 to 5 time constant, I can write it equivalent to like this only. Okay, so it will be Im RB over N L over R divided by Im RB over N omega. Okay, so we can see that phi DC max over phi AC max can be written as omega L over R. Okay, it is nothing but XL over R. Okay, this 2 pi f L over R is having a typical value of 20. Why? This thing 2 into 3.14 into 3. So L over R is having a value of approximately 3 for a normal power system, that we can see or derive from the relation which we have studied for the effective grounding also. We can have some idea, not the actual or exact part. Okay, so you see that phi max can range from 1 plus omega L over R value, since phi DC max is equal to omega L over R phi AC max. So I can write phi max to be phi DC max plus phi AC max, and I can put this value, I can find it out to be phi AC max. So you see that during the transient, the core of the CT may have to carry the flux which is around more than 20 times of the steady state, or the just that flux which should be there when this DC transient part is not available. Okay, so you see that to cater for this heavy flux, what we should do during the construction, either we should take the core material to be very high, that is we have excessive dimension of the CT, and if we cannot do that, then we should adopt some kind of special design, like we should introduce some kind of very small air gaps which do not interfere with the excitation characteristics of the CT core. However, we will study that air gaps have an equivalent effect of negative MMF. Okay, so what they will do, they will try to have an anti-remanence effect. Anti-remanence effect, what does it mean? It means that those small air gaps will try to have an effect that there is zero remnant flux available initially. So because of this DC transient is just going to have the effect. There will be no effect of the already available remnant flux. Okay, or we may include more air gaps so that the behavior of the core becomes linear. Okay, because of that, saturation effect will not come into the picture, linearity will still be there. But usually what happens, that the relays which are required to be acted on, they act very fast. They act within just one or two cycles of the initiation of the fault. So you see, initially this flux is not going into the saturation. Okay, this flux is also taking some time to go into saturation. So if our relays are fast enough that they act between this time only, before this saturation occurs, then we do not need any special design of the CT. Okay, so a fast response relay will help us in designing the specialized construction of CT. Okay, and now the overcurrent relays, they usually do not depend upon that much of the behavior of the current or the waveform of the current. They just depend upon the magnitude, and magnitude wise the value of current will still be very high available to the current. So overcurrent relays are not that much affected by the DC transient, okay, or the transient behavior of the CT. However, whenever we are dealing with the differential protection, then there will be different kind of CTs available on the one side and the other side of the protected equipment. Now this primary side CT and the secondary side CT may have different excitation curve. Small difference will be there in their excitation curve. Then because of this saturation occurring at different time in these two CTs, there can be a spillover current which can be directed by the differential relay, causing it to trip falsely, okay, during the transient. So in that case, we require a very fast relay such that it can detect the fault during the initial phase of the fault, or for the normal operation like switching only, we should try to desensitize the relay so that it should not trip during the transient part. Now these two things are contradictory in nature. That's why we have to plan for and design for the relaying system or the protective system such that these two contradicting requirements are fulfilled somehow or up to the maximum possible extent available with the current technology. Okay, now in one of the lectures we will also study about the available new technologies in the CT, like optical fiber CTs are now available, although these are not that much predominant as of now. They are just also now in testing stage or just kind of a demonstration phase type only. So it will take time to get easily available in all the power system, but we will study briefly about them. So if you find this lecture is helpful to you, then please share and subscribe my YouTube channel. Thank you.